Hello, hello, hello. This is Nicholas, and I am doing a generalized video on the variation of parameters. Now, I did a video on the variation of parameters for order n equals 2, but now, but now I'm going to do variation of parameters, and it's going to get pretty ugly, for order n. So the first thing we're going to assume, just like in the variation parameters for order 2, is that we have a particular solution y sub p, but instead of just being v sub 1 y sub 1 plus v sub 2 y sub 2, you can probably imagine it's going to be in the form v sub n y sub n. You know, v sub 1 y sub, we're adding n of these things together. That's going to be the form of our y sub p, and we're going to have to find n different v's in terms, they're functions of x's. And we also have to, if we're finding n different things, we need n different equations, so we have to oppose n different conditions on the variation of parameters. And the first n minus 1 follow a nice pattern. And so that pattern is, well, we start and we say that v sub 1, or we say y sub 1, v sub 1 prime plus y sub 2, v sub 2 prime is equal to 0. For the, just kidding, plus dot 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 plus y sub n, v sub n prime is equal to 0, because there's n of them. That's our first condition to make life easier, and then we say y sub 1 prime, v sub 1 prime plus y sub 2 prime, v sub 2 prime plus dot 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 plus y sub n prime, v sub n prime. We also assume that to be equal to 0 to make our lives easier. These are all to make our lives easier. And we go down and down and down, and there's n minus 1 of these, and we go up to the n minus 1th derivative of y times v sub 1 prime plus the, and this is y sub 1, plus the n minus 1th derivative of y sub 2 times v sub 1, times v sub 2 prime, plus dot dot dot, plus the n minus 1th derivative of y sub n times v sub n prime. And we want that to all be 0. And then lastly, like with our last condition for variation of parameters of order 2, where we had ay double prime plus by prime plus cy is equal to f of t, we want our last condition, which is going to be that my bad. This is because here there's actually n conditions. It's n minus 2, then minus 2th derivative. Yeah. This is n minus 1 conditions, because we start at the 0th derivative, or in other words, just the function. And then our final condition is that the n minus 1th derivative, v sub 1 prime plus the n minus 1th derivative, v sub 2 prime plus y, the n minus 1th derivative of n times v sub n prime, that's going to be equal to f of t over a, just like how it was in the order 2, just generalized. So this is the final condition. Now if that isn't ugly enough, just wait, it gets worse. Another necessary condition for the solution to the system in the interval, say we're solving the system in the interval, say x, in the interval x, which is, say, from a to b, in the open interval, is that the determinant of in other words, the solutions on this interval from a to b, they need to be linearly independent all n of the building blocks, all of the, all of the v sub 1, y sub 1, v sub 2, y sub 2, all of those need to be linearly independent to one another. So, in other words, what we're claiming is that the Wronskian of y sub 1 y sub 1 up to y sub n of these are, what do I want them to be functions of? I use f of t, so I'll use t here, is not 0 for all t that's on the interval a to b. Okay, so the necessary condition for the solution to the system is that the determinant of the Wronskian, made up of from v sub 1 prime to v sub n prime, that all the coefficients, in other words, the y sub 1 up to y sub n, and all those and I'm not doing a good job here, but this y sub 1 and this y sub 1 or y sub 2, everything in front of a y sub n prime can't be 0. So we want the Wronskian to not be equal to 0 of all the different y sub n's, but we also don't want any of the particular y sub n's or their derivatives to be 0 on the interval from a to b. So now we have this lovely matrix equation, and so we have y sub 1, y sub 2, up to y sub n, and all the way down to y sub 1 of the n minus 1th derivative. And we got all this Schmollschkin in between. So, and all this is going to be equal to the Wronskian of y sub 1 to y sub n of x. And so and this isn't a determinant. This is a matrix. So we now need to solve this equation here for v sub k prime, where k is somewhere between 1 and n. And using Kramer's rule, we would get that v sub k prime is f of t times w sub k of x, I'll say what that means in a second, over the Wronskian, I don't know why I wrote x here. I have a habit of doing that. It's t, of the Wronskian from y sub 1 to y sub n of t. And so w sub k, if you remember from Kramer's rule, w sub k is the determinant of w by replacing the kth column with in other words, we're doing a cofactor expansion on column k. So in other words, w sub k of x would be -1 to the n minus k times the Wronskian of it's everything from y sub 1 to y sub n, but just not including y sub k, because that's the column we're doing a cofactor expansion on. So that's what w sub k is. It's the determinant where we do a cofactor expansion along that column. It's the determinant of that really big matrix, if you can imagine it. For example, maybe to make it more concrete, if I had matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, then this isn't a Wronskian matrix, obviously, but what I mean by cofactor expansion, is that, so say we wanted to evaluate this determinant, and so we would do an expansion by minors, let's say in this column k equals 2. And so we would have a negative 4, because it's a plus, a minus, and then a plus. That's where the negative 1 to the n minus k comes from. So it's really, I guess technically, if I want to mirror my what I've written down better, I should write it as negative 1 to the 3 minus 1, 3 minus 2, because we're in k equals 2, times the determinant, so we have 4 times the determinant of 2, 3, 8, 9. So that's what I mean by a cofactor expansion along that row. And that's what Kramer's rule tells us to do. Instead of this, instead of this stuff here, instead of that, we have the Wronskian instead. Just because that's what we're dealing with. We're not dealing with just this generic matrix. So I hope that kind of makes sense. So now this means that y sub p of x we're multiplying y sub 1 v sub 1, y sub 2 v sub 2, y sub 3 v sub 3, and then we're summing them all up. So we have a sum, and it's going from k equals 1 to n of y sub k of x. Like y sub 1 times v sub 1, but v sub 1, or in general v sub k, is the integral, right? It's the integral of all of this stuff, because v sub k prime is all that stuff. So it's the integral of f of t times w sub k of x over the Wronskian of y sub 1 to y sub n of x. And this is y sub p. Now if we take that and we add the homogeneous solution, then we're at the general solution. I definitely think I should do an example for this. So let's do that. Let's do that example. Because it can get messy. So let me actually just bring this, see if I can't just copy paste it, because it is helpful to kind of have the formula right there. At least for me, there's so much unknown stuff going, there's a lot of unknowns. Okay, let's consider x cubed y triple prime plus x squared y double prime minus 2x y prime plus 2y is equal to x cubed times the sine of x. Well, one thing that you should do immediately is you should say, well, I don't really like that coefficient there in front of the y triple prime. I would want it in standard form, so I'm going to divide by it. And it's also nice to have an x cubed here, because that's going to go away. So we have y triple prime plus 1 over x y double prime minus 2 over x squared y prime plus 2 over x cubed y is equal to the sine of x. And so now we need to do some algebra. So first we should probably, well, first of all, let's identify some stuff. So this is f of t. F of t is just the sine of t. Now we need to find the Wronskian. So First, before any of that stuff, though, the Wronskian is made up of the fundamental set of solutions. So, right, that's what the y sub 1 up to y sub n mean. So we need to first set, let me just drag it like this. Or let me copy it. No, whatever, I'll just write it. Okay. Y triple prime plus 1 over x y double prime minus 1 over x squared y prime plus 2 over x cubed y is, and we need the homogeneous solution, so set this equal to 0. Now actually I think that's a, ooh, did they tell me what it is in the book? They in most differential equation books they would tell you what the fundamental set of solutions is, but this looks to me like a Cauchy-Euler equation of order 3, because if I multiply by x cubed, I get x cubed y triple prime plus x squared y prime minus x y, or this is double prime, minus xy prime plus 2y. And that is a Cauchy-Euler equation of degree 3. We would get, okay, here we go. The solution is going to be in the form y equals x to the r. So x cubed, I'm driving the characteristic equation. So we have x cubed r minus 1, r minus 2, times x to the r minus 3, plus x squared r minus 1, x to the r minus 2, minus x to the r minus 1 plus 2x to the r equals 0. So x to the r times r minus 1 times r minus 2 plus r times r minus 1. Sorry, times r minus 1 plus r plus 2 equals 0. Okay, oh my gosh. Okay, I'm going to just ignore that x to the r because I don't really care about it. So r squared minus r times r minus 2. That's giving us a r cubed minus 2r squared minus r squared plus 2r plus r squared minus r plus 2 equals 0. So r cubed, minus and a plus, those go away. Minus and a plus, those go away. Oh, well, r cubed minus, that wasn't as bad. Minus 2r squared plus 2r plus 2 equals 0. Does that have a root at -1? -1 minus 2 minus, no. Okay, let's see. Oh, no. I think it's time for Desmos. 1, -2, 2, 2. Okay. So I have a 1x cubed minus 2x squared plus 2x plus 2. All right, I'm just going to take their hint in the book. Okay, in the book, they told me that the fundamental solution set to the homogeneous solution was, oops, it was x to the -1, and x to the positive 2, x squared. So this now is just the homogeneous solution. We haven't even started finding the particular one yet. So now we need to find first the Wronskian of x to the -1 and x squared. And that's going to be equal to, we have the matrix x, differentiate 1, and then again 0. x to the negative 1, negative x to the negative 2, 2x to the negative 3. X squared, 2x, and 2. This is good yeah, this is where we are evaluating. Oh, I have to evaluate a determinant. Okay, so this is the matrix. Now we need to find its determinant. I have written down that it turned out to be negative 6x to the negative 1. You could verify that for yourself if you really wanted to, I guess. I doubt you will. Now we need to find w sub 1 of x, w sub 2 of x, and w sub 3 of x. And so w sub 1 of x, we do a cofactor expansion along the first column. So we have a negative 1 to the, we start out with a 3 by 3 matrix on column 1, so 3 minus 1 times. Now, we only are considering the x to the negative 1 and the x squared. So we have x to the negative 1, negative x to the negative 2, x squared, and 2x. And when we evaluate that, apparently we get, okay, wait. No, I'm going to do it. Okay, negative 3 minus 1, that's negative 1 squared, so that's a 1, so just get rid of that. Okay, so we have 2 plus 1, 3. That was nice. Now the second one, we're going to have a negative of the determinant because it's negative 1 to the 3 minus 2. And now we are doing a cofactor expansion along the x to the negative 1 column, so we ignore the x to the negative 1 and we just have an x and an x squared. That's a 1 and a 2x. And that is easy enough to do. That's 2x squared minus x squared. So 2x, that's just negative x squared. Okay. And let me write that a little better. Negative x squared. Okay. Now, w sub 3, 3 minus, we're on the third column, and it's a 3 by 3, so that's negative 1 into 3 minus 3, or 0, so it's just positive. Now we just have the x and the x to the negative 1. So that's 1 and negative x to the negative 2. So negative x to the negative 1 minus x to the negative 1, negative 2x to the negative 1 is that determinant. Okay, so our particular solution is, okay, we do y sub 1, which is x, times, now we have an integral of f of t, which was sine of x, or yeah, sine of, I'll call it f of x, sine of x, f of x times now Wronskian sub 1, which is 3, over the total Wronskian, which is negative 6x to the negative 1. Plus, now we have x to the negative 1 times the integral of sine of x still, times x squared over still a negative 6x to the negative 1. And then we have plus x squared times the integral sine of x times negative 2x to the negative 1 for negative, yeah, that's a negative, okay, negative 6x to the negative 1. Now I have to do all these integrals, and I still haven't found the general